Okay, so imagine this for a moment. You're living your entire life, thinking reality works in a certain way. Objects have positions, things happen in order, causes come before effects. Everything feels solid, predictable. Now imagine discovering that none of that is actually true. Number 10, the sentence that says everything. In 1965, a physicist named Richard Feynman said something that still echoes today. I think I can safely say that nobody understands quantum mechanics. He wasn't joking, and he wasn't exaggerating, because here's the paradox. Quantum mechanics is the most accurate theory in the history of science. Its predictions match reality with precision beyond anything else we've ever created. And yet, its meaning, its implications, make absolutely no sense to the human mind. Particles can exist in two places at once. They can behave like waves and particles at the same time. Two objects can affect each other instantly, even across vast distances. And simply observing something changes what it is. These are not ideas. They are experiments, repeated, verified, used. The problem isn't the math. The problem is that reality doesn't care what feels intuitive to us. Number 9, the experiment that broke reality. At the beginning of the 20th century, physicists were confused. Light didn't behave properly. Sometimes it acted like a wave, other times like a particle. It couldn't be both, but it was. Then came the most famous experiment in modern physics, the double-slit experiment. You fire tiny particles, like electrons, toward a wall with two openings. If they were normal particles, you'd expect two lines on the other side. But that's not what happens. Instead, you get an interference pattern, like waves overlapping in water, as if each particle passed through both slits at the same time and interfered with itself. Now here's where it gets disturbing. If you try to observe which slit the particle goes through, the pattern disappears. It behaves normally again, as if the act of looking forces reality to choose. This isn't philosophy. This is measurable, and it means something simple and terrifying. Reality behaves differently when it is being observed. Number 8, entanglement, the impossible connection. Even Albert Einstein didn't like this, not because the theory failed, but because of what it implied. There's a phenomenon called quantum entanglement. Two particles linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. Einstein called it spooky action at a distance because it seemed impossible. Nothing should travel faster than light. Nothing should connect objects like that. So he assumed quantum mechanics must be incomplete. But then, in 1964, John Bell proposed a way to test it, and in 1982, Elaine Aspect performed the experiment. The result was clear. Einstein was wrong. Entanglement is real. There is no hidden signal, no delay, no trick, just a universe where distance doesn't always matter. Number 7, the race that already began. This isn't just theory anymore. It's a global race. Governments and companies around the world are investing billions into quantum technology. Not millions, billions. Because quantum computing is not just faster computing. It's something entirely different. A classical computer uses bits, 0 or 1. A quantum computer uses qubits, which can be both at the same time. This allows it to explore multiple possibilities simultaneously. Problems that would take classical computers millions of years could be solved in minutes. And that's why this has become the next technological frontier. Not in 50 years, now. Number 6, the moment everything changed. In recent years, something happened. Not a theory, a result. Quantum systems began solving problems that classical machines simply cannot handle. Companies like Google, Microsoft, and others started reaching what's called quantum advantage. For the first time, a quantum machine performed tasks that would take traditional supercomputers an impossible amount of time. We're talking about calculations that could take thousands or even millions of years, done in minutes. It's not perfect yet, it's not scalable yet, but the barrier has been crossed, and once that happens, there's no going back. Number 5, the problem no one talks about. There's something else, something most people don't realize yet. Your data, your messages, your entire digital life is built on a fragile assumption that certain problems are too hard to solve. Modern encryption depends on this. It protects your bank accounts, your private conversations, military systems, entire financial infrastructures. And it all comes down to one idea that factoring very large numbers takes an impossible amount of time. For classical computers, it does. It would take millions of years. But a sufficiently powerful quantum computer wouldn't need millions of years. It could do it in hours or less, which means something unsettling. Not that your data can be hacked today, but that it can be stolen now and decrypted later, stored, waiting until the technology catches up. Governments already know this. That's why they're racing to develop something called post-quantum cryptography, new systems designed to survive a future where quantum computers exist at scale. Because this isn't theoretical anymore. This is preparation. Quiet, global, urgent preparation. Number 4, the medicine of the future. Now imagine taking that same power and applying it to something closer, something human. Medicine. Right now, developing a new drug can take over a decade, sometimes longer, and cost billions. Not because we don't know what we're doing, but because the problem itself is too complex. At the molecular level, everything follows quantum rules. Atoms interact, electrons shift, bonds form and break in ways classical computers can only approximate. They simulate, they guess, but quantum computers don't approximate, they replicate. They can model molecules exactly as they behave in reality, which means something extraordinary. Instead of testing thousands of possibilities blindly, we could predict the right one from the beginning. Faster treatments, more precise drugs, fewer side effects, and earlier detection, because quantum sensors are being developed to detect changes in the body that current technology simply cannot see. Diseases identified before symptoms even appear. This isn't a distant vision. It's already being explored by companies like IBM and Amgen. The real question isn't if this will happen, it's when it becomes normal. Number 3, the medicine of the future. Now imagine taking that same power and applying it to something closer, something human, medicine. Right now, developing a new drug can take over a decade, sometimes longer, and cost billions. Not because we don't know what we're doing, but because the problem itself is too complex. At the molecular level, everything follows quantum rules. Atoms interact, electrons shift, bonds form and break in ways classical computers can only approximate. They simulate, they guess, but quantum computers don't approximate. They replicate. They can model molecules exactly as they behave in reality, which means something extraordinary. Instead of testing thousands of possibilities blindly, we could predict the right one from the beginning. Faster treatments, more precise drugs, fewer side effects, and earlier detection. Because quantum sensors are being developed to detect changes in the body that current technology simply cannot see. Diseases, identified before symptoms even appear. This isn't a distant vision. It's already being explored by companies like IBM and Amgen. The real question isn't if this will happen, it's when it becomes normal. Number 2, it was always there. Here's the part that changes perspective. Quantum mechanics is not new. It's not something that's about to arrive. It's something you've been using your entire life. Every electronic device you own depends on it. The transistor, the tiny switch inside every processor, works because of quantum effects. Without it, there is no computing, no smartphones, no internet, no modern world. The same is true for lasers, used in communications, in surgery, in measurement systems. Even medical imaging, like MRI scans, relies directly on quantum principles, which means something simple. The quantum revolution already happened once, quietly, in the background. What we're seeing now is the next layer, the one that becomes visible. Number 1, the question we still can't answer. After everything, after a century of perfect predictions, working technology, and real-world applications, there's still one question left, and it's the most important one. Why? Why does it work? Why does reality behave this way at the smallest scale? We can describe it, we can calculate it, we can use it, but we can't explain it. Not completely. There are interpretations, different ways of trying to understand it. Some say reality splits into multiple universes. Others say outcomes don't exist until they're observed. Some suggest deeper hidden variables. Others reject that entirely. But here's the strange part. They all predict the same results, which means we can't tell which one is true, or if any of them are. So we're left with something rare, a theory that works perfectly and still feels incomplete, a system that describes reality without telling us what reality actually is. The most unsettling part isn't that the universe is strange, it's that we've built tools powerful enough to prove it, and we still don't understand what we're looking at. And remember, the universe doesn't reveal its secrets to those who rush. It reveals them to those who know how to look. Subscribe and keep listening to the silence.